This is my Physics 2212 Lab 3 circuits. So the purpose of this lab is to predict the behavior of circuits with ohmic resistors in series and parallel, as well with capacitors. It will be using multimeters to measure the conventional current and the potential differences, and it will also involve using principles of energy conversion, like the loop rule, and current conversion, the node rule. So just to recap on the physics concepts, the node rule is by conservation of charge, the electric charge cannot be created nor destroyed, therefore the current flowing into an area must be equal to the current coming out. And the loop rule just states that the round-trip potential difference for static electric fields is zero due to path independence. Ohm's law also states that for ohmic resistors, the potential difference across a resistor is equal to IR, so therefore V is equal to IR. Here's just a brief preview of the main results. On the left, we have a capacitor discharging in a RC circuit, and then on the right, we have all the data points that we calculated. Here's the experimental setup and predictions. So for all experiments, the system is the entire circuit and its components, and the surroundings is nothing. Here is a diagram of the first circuit on the left here, and on the right, we want to predict what the current values for I1 and I2 are. Using the node rule and the loop rule, we can calculate that the IR is equal to I2, which is equal to 0.02 amps. If we implement this in the simulation and then find out what the current is, we get that both the ammeters show that the current is 0.02 amps. Therefore, the prediction were right. But if we changed one of the ammeters and then made it backwards, there would still be no change, and then the current would still be the same. Now, if we remove one of the ammeters and we replace with a voltmeter, the ammeter will show a 0 amps because the voltmeter has a very high resistance, and the voltmeter will show a negative 3 volts due to a very high resistance resulting in zero flow. So now we have this circuit. We remove the voltmeter and then just place a straight wire, and we only have one ammeter. If we want to calculate all of the individual parts separately, we can use a voltmeter and then calculate what the potential differences is, which is shown here. And then we can also plot that difference on this chart that I made here. And just as a sanity check, we know that the loop rule indicates that the difference will be zero, and that is what we get when we add up all the individual potential differences. So what if we add an ammeter in the parallel with the 100 ohm resistor? If we do that, then the current actually increases due to the ammeter being in parallel having such a smaller resistance compared to the 100 ohm resistor. So then we can see that the current increased to 0.06 amps. When we want to calculate the resistance of the circuit, we can use the individual potential differences calculated earlier with the voltmeter, and use this formula where R is equal to the difference, the potential difference over I. And what we get is that the 47 ohm resistor has a resistance of 48, the 100 ohm resistor has a resistance of 102, and then the wire and the ammeter both have a resistance of 0 ohms. So now we have a RC circuit. When we connect the battery to the capacitor and the capacitor to the light bulb, we get that the light bulb goes off when the capacitor is fully charged. When the capacitor is used as a battery, which is shown on this right picture, then the light bulb starts to light up again. However, as the capacitor both charges or discharges, the current decreases to 0. So here are the timings of the charging and discharging. For a 10 ohms, charging takes 15.2 seconds, and then discharging takes 19 seconds. For 20 ohms light bulb, charging takes 26 seconds, and then discharging takes 50.7 seconds. And here's the pictures of both the discharging circuits. Now, when we use a voltmeter and then take the voltages for a RC circuit with a 9 volts battery, 30 ohms light bulb, and a 0.2 F capacitor, we can track it and get this graph here. When we find the experimental RC, we get that it is equal to 5.988, and then the predicted is equal to 6. So we have a very close value from the experimental and the predicted. So possible errors are imprecise timing measurements, and then another is that simulation doesn't always match real-world results. So what if we did this in the real world with the actual ammeter? Well, a real ammeter will have a non-zero resistance, and it will have some sort of impact on the real current flowing in the circuit. What if we did this in real life with a battery and a capacitor, but with no resistor? Well, in theory, the capacitor should charge instantly to the battery voltage if there is no resistor. However, in real world, even the batteries and the wires have some sort of non-zero resistance. That's it for my lab, and thank you for watching.